Okay, good morning, everybody. So, after finishing two exams, the second exam, how was going with the second exam? Is everything okay? Very difficult or easy? It's okay? It's okay. Hopefully you can have a good score. I don't know. Yeah. Okay, so we will continue our lecture. Actually, we finished one example regarding the sensor design, right? Accelerometer design. I think that will be very useful for everybody for your future research or for your future study. And now we are going to move into the next topic. So the next topic will be regarding one kind of actuator. It's a conjugate actuator. It's also a very important, devices which has been developed in the past 20 years. And this actuator cannot be only used as an actuator. It can be used as a sensor as well. Okay, so so in these 2 weeks, 2 or 3 weeks, we will focus on this kind of sensor. And also in your final project, actually, they will be also useful. If you are going to design like an actuator related things, you definitely need to understand the principle of this kind of electrostatic conjugate actuator. So before we go to the detail of the actuator design, currently I want you to focus on the process. Okay, so the process flow will be a little bit different from the previous. We talk about the CMOS process. So here we will introduce you another process we call the MUMPS process. MUMPS means a multi-user, multi-purpose. So that means everybody can put their design onto the same wafer for fabrication if they share with the same fabrication process. So in this MUMPS structure, the process, the material you can have is exactly as I show here. Actually, it consists of two important major structural material, including polysilicon 1 and polysilicon 2. So there are in two structural layers, and among them there are two other oxidation silicon dioxide layer. There's a sacrificial layer because it's based on the surface micromachine process. So we have learned about the surface micromachine process a couple months ago regarding how to deposit material layer by layer, and by using sacrificial layer to separate them. And then at the end, we take out the sacrificial material and obtain the structural material. Then we get the final released structure. So actually, this kind of structure has been developed for a couple years until they finalize the thickness of a layer. So including the polysilicon 1, around 2 microns, pretty thick. The second polysilicon is 1.5 micron, a little bit thinner. But when you compare these two polysilicon, the thickness compared to the original CMOS process, the polysilicon layer, actually is much thicker, right? The original polysilicon structure is only like a 1 micron at most, 0.8 micron. So here, if you combine these two structures together, you can easily get a 3.5 micron. So it's much thicker than before. And also two sacrificial layer. One is oxide one, is also very thick one, 2 micron. So in the past, we don't apply the sacrificial layer so thick. So the purpose to give a so thick sacrificial layer is because after releasing, we want to leave some room here. If you have some structure want to do rotation. So if you don't have enough room underneath here, you won't be able to do rotation, the action of rotation. So that's why 2 micron, I think is at the compromisation. If you put it too thick, actually deposition process cannot allow you to deposit too thick the material. If you put it too thin, the structure won't be able to rotate. So at the compromisation, so any other people find the 2 micron may be acceptable thickness for both the fabrication reason and also the functional reason together. So these two layers are the major two layers. So beside these two layers, actually there are several other layers for supporting the structure and also do electrical connection. For example, the bottom one. You see the bottom one, there's another polysilicon we call the poly zero. The poly zero, the thickness is only 0.5 micron. Actually, this layer is not very thick. Okay, the purpose for this layer is not for doing structure. It's not structure layer. So the poly zero is mainly for electrical conduction. So you want to connect the electrical signal into the structure. So you can by using the bottom poly zero layer. So under the poly zero layer, there's a thick silicon nitride layer, 0.5 micron. It's actually silicon lustrous nitride. So silicon nitride layer, as before, we mentioned in the CMOS process, similar to the silicon oxide layer, is for insulation, to insulate the electrical signal, to prevent the shorting from the poly zero to the substrate. Okay, so silicon nitride is the insulation layer. So on the bottom, we have poly zero as an electrical connection layer. Actually, according to our CMOS process, actually, usually we will have 2 layers of electrical conduction, right? If you want to connect the signal horizontally and vertically in 2 different pathways, you definitely need 2 layers, not only 1 layer of a metal connection. Here we don't allow 2 layers of metal. However, on the bottom we have a poly zero as 1 layer, so you can connect electrical signal from the bottom to 1 direction, and the other one is on the top. Okay, so on the top you can see there is a chromium and gold layer. So the chromium is a material for adhesion, so to improve the adhesion between the gold and the bottom material. So the major electrical conduction layer is the gold layer. So it's around like 0.5 microns, pretty thick. Okay, so now you have an electrical connection not only on the bottom but also on the top. Okay, so you can make a network, one from one direction, the other from the other direction. However, these 2 layers are not all are metal. Only the top are metal, so the top metal one can be used to connect to longer distance. But the bottom one, poly zero, the resistance is pretty high, so don't use that to connect it to far distance, electrical connection. Only for short distance connection. Okay, like before, we mentioned in the CMOS process, the poly gate, we don't extend the poly gate to a long distance for connection. Okay. So this is a MUMPS structure. So if you don't do anything, don't do any mask castings, after deposition, you got 1, 2, 3, 4, 5, 6, 7 layers here. The total thickness is around 7 micron. Okay, it's much thicker than before. And if you do some masking process, the possible connection can be like this. So, for example, the first polysilicon, if you puncture holes on the first superficial layer, actually, after deposition of the first polysilicon, the polysilicon layer can be anchored on the bottom of the poly zero, even the poly zero to the bottom silicon nitride. So when this layer connects to the poly zero, so you are able to connect the electrical signal from the poly zero, then go to the first layer. Okay. If you anchor the first polysilicon onto the silicon nitride, in that case, you won't get any electrical signal from the bottom. But instead, if you put a metal on the top, you can use the metal to connect your electrical signal to the top layer. Okay. So this this is a second layer. The first layer. The first layer can be either anchored onto the poly 02 or anchored onto the silicon nitride. Depends on your masking design. So we will discuss that in detail later. The second polysilicon layer, as we mentioned before, is a little bit thinner than the first polysilicon layer. And if we puncture the holes on the second superficial layer, so the second polysilicon, poly 2, can be used to connect to poly 1. Okay, so you can connect these 2 structures, become a very thick structure. In total, you will have a 3.5 micron in thickness. You also can connect the second polysilicon layer not only to the poly 1, but to the poly 0 or to the bottom substrate as well. For example, this example show you the second polysilicon layer is connected onto the silicon nitride, the insulation layer, so there won't be signal coming from the bottom. Instead, the metal on top can be used as a connection to connect the signal to the second polysilicon layer. So the metal layer can be used not to contact with a poly 2, but also can be used to connect poly 1 as well. Depends on if you open a hole here and deposit metal at this area, you still can do that. Okay, so this shows you some flexibility of how to do the connection among them, and also you can use them high flexibility to make a thicker fin or thinner fin, depends on your application. So this process can be used to fabricate the electrostatic motor, as we mentioned before. We mentioned 2 different versions of electrostatic motors. In the first, I think it's in the second or third homework, right? So you have been working on how to develop the fabrication process for one kind of electrostatic motor. The motor has the rotor and the stator using electrostatic signal to drive them. And so in this case, you can readily use this kind of fabrication structure to facilitate that kind of device. Okay, so something in addition to the structure information, related information, so some information you need to notice is the first is the substrate. Actually, we are not drawing the substrate. Actually, there's a very thick silicon substrate layer on the bottom. Okay, so we are not drawing that. So we draw the structure starting from the insulation layer. That means the silicon nitride. Actually, there are still some doping different materials inside the substrate material. So we will see that later. So the substrate material we used is 100 millimeter. It's a 10. It's like a 10-inch wafer, N-type, 100 silicon wafers, and the resistivity is a medium. It's a 0.5. Okay, it's not very high, it's not very low. It's medium. And the substrate surface, you need to notice, will be doped heavily with some kind of phosphorus to reduce charge problem. Because every time when you send a signal into the poly 0, actually some induced charge will occur on the bottom of the substrate. So after you take out the charge on the top, however, the charge may remain on the bottom surface if you don't have a good conduction. Okay. Originally, the silicon substrate only have 0.5 ohm CN resistivity. It's pretty high. So according to the RC time constant, if you have a very large resistance and you times the capacitance of this device, so finally you get a very long time to take out the charge. When you have the charge on this kind of material, you take a long time to retrieve your charge. So there will be some charging problem. So that's why close to this surface, there will be heavily doped layer. So in order to increase the conductivity, reduce the resistance, okay? So in that case, the RC time constant will be lower. Do you understand? R times C, the square R times C means the time constant. If you want to charge onto one kind of material or take out the charge from that material, you need to take some time. Okay, the time depends on the resistance and also the capacitance. Okay. Okay, so the surface will be heavily doped. It's not showing here, so we will see this kind of doping later. Okay. Okay, that's the basic structure. So now we will go to the detail of the fabrication as before. And so after we understand the detail of fabrication, then we can use this fabrication and also the materials to design our real structure and also device. Okay, So as we mentioned, we started with the N-type silicon substrate, okay? And also, first we need to dope the very heavily doped phosphorus layers, as shown here, the lighted colored layers here. So, so in this case, we can increase the conductivity below the silicon nitride layer. So after this layer doping, and we have silicon nitride deposition on top of this kind of heavy doped layer. So the thickness is around like 0.5 microns, pretty thick. The reason for this kind of thickness is actually in the rest of the process, we will heavily use a lot of RE etching, the dry etching method to do the pattern. The dry etching, actually, the selectivity is not high. It's not very high. So when you want to take out the material, as we have one homework in our first homework regarding the CMOS process, if you want to do some etching on top of another material, you need to consider the bottom material, if this kind of etching will harm the bottom material, right? The over etching condition. Okay, so in order to allow the over etching condition more flexible, so in this case we have a very thick silicon nitride layer for protection, okay, to allow you to have enough room for the dry etching process, okay. So there's a reason for the thick silicon nitride layer. Then on the top, deposit poly-zero material. So these three layers, we don't need to do any pattern. But the poly-zero will do pattern later on, but the silicon nitride will be used to protect the whole surface. So we don't take out the silicon nitride all the time, okay? And also the dopant on the bottom, we always have the dopant everywhere on the wafer, okay? So only the poly-zero, after deposition, you can do patterning, okay? The second step, we do RE patterning, poly-zero. So here we use the max number 1, okay? It's showing here. So after the first layer, the poly-zero patterning, then we deposit the first superficial layer on top of the surface. It's 2 micron, okay? Then we apply very interesting things as different from before. We're using RE etching to etch halfway, not all the way, onto the first superficial layer. So the thickness of the etching is only 0.75 micron, pretty thin, okay? Only a little bit. So the purpose is not to make the material connect to the bottom, but make the material a little bit extrusion from the bottom surface. So the purpose is for to reduce, if you have some structure release from the surface, and you want to decrease the contact area between the structure and the bottom surface, you make a we call the dimple structure on the bottom later on, okay? So these 2 dimple will contact with the surface with a minimal contact area. So that can reduce the friction problem. Okay, most of people don't. We will show you later, okay? So remember, this RE patterning process won't give you a long etching process, just halfway. So you have a little bit, holes here, okay? And after that, we pattern the first superficial layer. Then we go to deposition of PSG hot mask, actually. Polysilicon, then PSG hot mask. The first polysilicon then deposit onto the superficial layer, on the top of the superficial layer. Then we deposit another PSG hot mask. The purpose for this is we want to do axial doping, because this first poly, when we deposit first poly, is not conductive, it's not doped. Okay, so we use the bottom superficial layer and top superficial layer, because inside these 2 superficial layers, they are phosphorus, or has I think it's boron, phosphorus. It already has phosphorus inside the silicon oxide layer. So when we do axial annealing process, the phosphorus in the bottom and the top superficial layer, they will be diffused into the structure layer, the polysilicon structure layer. So this process we call it ex situ doping process. Do you remember ex situ? Means we are not doing the doping during the deposition of polysilicon. We do the doping process after we have the structure layer, then we do the doping. So it's called ex situ, not in situ. In situ means at the same time. Ex situ means afterward. Do you understand? 就是之后再做的。